Welcome. In this video, we're going to start our discussion on these mathematical objects called groups that we're going to be spending quite a few weeks looking at. So this video is just by means of an introduction to try and give you a bit of an idea for what a group is and what we might expect to be doing with them. So essentially, a group is or involves a set of mathematical objects and some kind of operation that combines them together. So for example, if we just take numbers, we are quite used to the idea that if we take, say, the integer 3, we can add two integers together and we get another integer 5. So we have a group. In this case, the group is Z, which is our notation for the integers. I'm using the word group before I've actually talked about what it means, but that's okay. And the operation in question here is the operation plus. So what does that do? Well, structurally, it takes in two of these integers and it produces another one. Now, do we always get this kind of property? Well, what if our set of numbers was, say, odd numbers? If I take two odd numbers and add them together, then I get an even number, so I don't get something in my set. So we need to be careful that when we're dealing with a set of things and an operation, that the operation needs to give us back another member of that set. So for our odd numbers, we can't be considering the odd numbers under addition to be a group. Again, we'll talk about what a group is a little bit later, because the operation is not closed. So the first thing that we're going to sort of have a crack at coming up with a slightly more mathematical definition of is what this kind of operation is. So here we've got two members of the set, and we've got not odd, which means that our operation plus is not closed. Okay, it doesn't give us a member of the set in question. So this operation plus, in the first case, which is fine, is what we call a binary operation. So a binary operation is an operation where you take two members of your set, you combine them together, and it always gives you back a member of your set. In our second example, plus is not a binary operation because when we combine two elements together, we don't get something back from our set. Okay, so on the next slide, I will show you the mathematical definition of a binary operation, and we'll chat about it for a second. And here it is. This is the definition of a binary operation. We'll go through it slowly and discuss some of the sort of key features, because this is quite a formal mathematical statement where every little piece of it actually needs to be there. So the first part, let G be a set. So G is just our set. For the previous examples, G was the set of integers, or for the first one of those. So a binary operation on G, okay, so we have an operation that's associated with our set G, is a function that assigns each ordered pair of elements of G. Now what does that mean? Well, it means if we take two things out of G, so for example 3 and 5, we can consider them to be an ordered pair. Okay, now order, so binary operation includes the notion of order. So it may well be that 3 plus 5 is not the same thing as 5 plus 3 when we look at more complicated sets and operations. I mean, an obvious example would be if the set was the set of square matrices and the operation was multiplication, then the order of the operation is going to give us different elements. Okay, so we're considering ordered pairs, or at least we're allowing ordered pairs, and it associates with each one of those an element also of G. So for our plus, it takes the ordered pair 3, 5, and it produces the element 8. Just so happens that with addition on integers, if we took the ordered pair the other way around, it also produces 8. So it's not excluding things like addition, which don't matter about order, that they're a subset of this idea. Okay, so the key thing is, though, is that it assigns an element of G to the pair. So if G was our set of odd numbers, we cannot have plus being a binary operation because plus does not assign to the numbers 3 and 5 an element of G. It doesn't assign an odd number to it. Okay, so normally we'll just write 3 plus 5 equals 8, but we'll just bear in mind that this plus operation is taking in 3 and 5 and it's spitting out the number 8. Okay, now we're now going to look at a slightly less conventional example, and this is the same example that Gallian uses in chapter 1 of the textbook that we're using in the course. So what I'd like you to do is take a moment, grab a square of paper. You may need to cut a rectangle into a square. And to help us understand this, it's really useful to have this on hand. So get your square of paper and label the corners A, B, C, and D, like I have in the little corner down there in the bottom right hand corner of the screen. Okay, so what I want you to do is to also make sure you have a front and a back to your paper. On the reverse side, label the corners also A, B, C, and D, but label them in the same places. So if I flip this over, A, B, C, and D are going to look like they're in that order there. That's because A on this upper right here is in the same place as A is on the other side. Likewise, B and B, they're in the same spot. Okay, and so you've got a natural front and back of your paper. So just pause the video, go away and grab one of these because it's going to be really useful to have that available to you to work on this. Alright, so hopefully you've now got yourself a square of paper. Now what we're interested in studying here is what we call the symmetries of the square. So we're asking the question, what geometrical transformations can I do that leave the square essentially untouched? I.e., I want to pick the paper up, do something, and put it down in a new configuration that still makes a square in the same spot. So for example, I could rotate it around 180 degrees. It's still the same square. Okay, it's still got the corners in the same place. So that would be one possibility. So how many of these possibilities are there? Well, there is one here. There's another one if I turn it around 90 degrees. Again, another 90, another 90, and then I'm back to where I started. So on the front of the paper, there are 4 possible configurations of our square that leave essentially the shape of the square untouched. And then if I turn it over, there are another 4. Okay, there's basically flipped over, and then there are 4 different ways it can be oriented on the back as well. So in total, there are 8 different orientations that our square can have. And the way I'd like us to think about these is, I'd like to think about each one as some kind of transformation from the home position like we've got here. Okay, so what we're going to do is we're going to imagine our square. We've got the square A, B, C, D here, and we want to imagine an operation, some kind of geometrical operation, that will take our square from this position to each of the 8 configurations that we've come up with. Okay, so the most basic one is what we call the do nothing operation. Okay, and I'm going to call it R0 to stand for a rotation of 0 degrees. Okay, so A, B, C, and D just get left exactly where they are. And I'm going to go through the 4 front configurations first because they're kind of the easiest to describe. Starting here, my next configuration is going to be the one I get if I rotate by 90 degrees counterclockwise. So just looking at the picture there, I've now got A down here, B's come up here, and I have C and D here. And if I'm thinking about this as a single operation from where I started, that looks like a rotation of 90 degrees anti-clockwise. So I'm going to call this one R90. I can continue in the same vein. Let's just make that look a bit better. If I rotate it a further 90 degrees, that can also be done in one hit from the starting position by a 180 degree rotation. So this one I'll call R180. And I'll label the corners as they now appear in the new position, A, B, C, and D. And finally, you can see that the last configuration is a 270 degree or minus 90 degree rotation from the start position. So we'll call this one R270. Okay, and now I've got A, B, C, and D, like so. Okay, so that's the 4 configurations on the front. Now I want to think about how I can get to the back with a single geometrical operation. Okay, so let's make some more positions for us. So my first one, I'm going to get to my first one just kind of arbitrarily by flipping my paper over horizontally like so. Okay, so we can sort of visualize this operation as a flip along that axis, and because it's a horizontal axis, I'm going to call this operation H, and that gives me the configuration A down the bottom. Nope, that's not right, sorry. A here, B, C here, and D. Okay, so maybe we can get to all possible positions by flipping along different axes. So rather than starting where we just were and rotating it different amounts, that's kind of like two transformations. It's a flip over and then a rotation. We want to see if we can do it in a single hit. So let's now try what happens if we flip our paper over vertically. And while I'm doing this, you might think about how we might get the other two. So this time I've flipped it along a vertical axis. So I can indicate that with a dashed line down here. I'll call this operation V, and we can see where the corners have ended up. We have A, B, and then we have C and D this time. Okay, next up we have got two more positions we have to reach. The other two are rotations on the back there. So if you've been thinking about this for a moment, maybe you've come up with a flip along one of the diagonals. So what say we now flip along this one here, and I'll call this D for diagonal. So I'm going to flip my paper along that diagonal axis along here, which will put it in this position. And let's record where the corners have ended up. So we now have A, B, C, and D. And we have one more configuration that we need to reach. Okay, again, we're starting in our home position, and we want to find the remaining position on the back. Again, maybe think about this for a second before you go on, but the answer is going to be a flip along this axis here. And we'll call this one D prime. Okay, so that's this axis along this way. I'll flip it over. And my positions are going to be A, B, C, and D. Neat. So what we've done is we've come up with a type of transformation that can bring my square from its starting position, this one here, to any of the possible 8 configurations that we came up with for our square. Okay, so the key point that we're going to talk about now is we're going to consider these sets of transformations, these 8 transformations, to be the set that we want to work on. So remember we talked about a group as being a set with a binary operation. Our set is going to be the set of the transformations. Okay, so the set is the 8 transformations. Okay, so it will be R0, R90, R180, R270, and H, V, D, and D prime. Okay, so I always indicate a set by putting curly braces around the outside of it. Okay, so we now have our set. Next thing we need to do is to think about how we can combine members of our set to give a new member, to give another member of the set of transformations. So how can we combine 2 of these transformations to make another one of these transformations? So the way we do this is to essentially take the 2 operations, say R90 and V, and then just perform them one after the other. That will give us a new configuration of this square, which will be represented by one of the transformations from home. Okay, so let's see how this is going to work in practice. So I want to be able to compose 2 transformations, and that should give me a third one. So let's say that I want to take my square, and I want to do R270, then D. Okay, so I've got A, B, C, D. Here it is, A, B, C, D. If I do R270 on this, you can consult the table on the previous slide or just do it. Okay, that's 1, 2, 3. Then I get the configuration A, B, C, D like this. Okay, that's my R270. And I then, let's say I do the transformation D. So remember D is our flip along this axis here. So I'm going to now, after having done R270, I'm going to flip this over along that axis, and I'm going to record the configuration that I have. So I now have the configuration A. This is where it's become very useful to actually have the piece of paper in front of you. A, B, C, and D. And the question is, what transformation is this? Well, so just have a look at it for a second. You can consult the chart if you wrote it down before. Can I get from my home position here to this position here in a single operation? Well, yes, I can, because we detailed an operation for every position that we can come up with. And it turns out that the operation that gets us from A, B, C, D in the original space to our end result is a flip along the horizontal axis. So let's do that again. A, B, C, here's our home position. If I flip this horizontally, I get C, D, A, B, and that is exactly the same as if I did R270 and then D. So that is H in one single step. Okay, the way we write it is we write D R270 is equal to H. Now you may look at that and think, hang on, you've written those back to front. We did R270 first, and then we did D, and that gave us H, but you've written them back to front. Well, it's not actually the way. The reason we write it this way is because we're thinking of it as function composition. So the way that maybe I would think about this is I would think of it as saying, like, as we're doing the function D, because remember this is like a function on the square, and then we're doing the function R270, and we're doing that function of a square, and then once that's been evaluated, we then do D to it. So you take the square, you apply R270, it's like the inside function, and that's the same thing as doing D R270 of H. Okay, so of the square, sorry. So the way in which you think of it is, if you think of there being some kind of thing on the outside that you're operating on, the one closest to it is the one that gets applied first. So when we say D times R270 equals H, the one that actually gets applied first is R270, so do first. Okay, so now we've got a weapon at our disposal which lets us combine two transformations, and it gives us a third transformation which is just the composition of the two. This is our binary operation that we're going to use to build hopefully this group that we're talking about at the moment. All right, so how does that work? Well, we can draw up a little table to help us. Again, if I were to indicate the one I just did, which was D times R270, I go from D across to R270, and I get H. So the thing to remember is we do these first, and we do these one second. So let's just do another example. Let's do, maybe we'll do V times R90 equals. Okay, so remember we do the one on the right hand side first. So R90 is rotate left by 90 degrees, and then we'll do a vertical flip. And this gives us that V times R90 gives us the configuration A, B, C, D, which is the same as we would have got if we had just flipped this along this axis along here, which is our D prime. Okay, so V times R90 is equal to D prime. Again, we do the one on the right first, so R90 first, then V. That gives us overall D prime. So we'll go to our table and fill in V times R90. That gives us D prime. Okay, so if you've got 5 or 10 minutes, Now would be a good time to actually see if you can fill out this entire table, this multiplication table for our set yourself by just working with your square of paper. So it's worth pausing the video and doing this because it gives you a real feel for how this thing works. But for those of you who are impatient, I will put it up shortly on the next slide. And here it is. This is the multiplication table for our set of elements. This particular set is called D4, and that's short for the dihedral group of order 8, where 8 is 2 times 4. So dihedral group order 8, which is 2 times 4. Okay, the order of a group is just the number of things in it. And the multiplication table is called the Cayley table, after the mathematician Cayley. Okay, so hopefully you had a go at doing this yourself and you managed to come up with the same thing. If not, that's fine. Here it is. So you can see that it's given us a composition for every pair of elements. We figure out what the corresponding one is, and that gives us this entire table. Because the composition of transformations is a binary operation, this was well defined for any particular choice of transformations I chose, and so we were able to fill in the whole thing. So the last thing we might want to do before we finish this video is just look at this table and see if we can see any interesting features. Perhaps the first one that jumps out is that it's kind of partitioned into blocks where we've got these rotations here and other things here. Now we'll study what that means a bit later on in the course, but let's just maybe focus our attention on rows and columns and see what's in each one. So we can see, to start with, every row and every column have each member once. Each transformation once. Okay, nothing appears twice in any particular row or column, which is a good thing. This R0, which is like the do-nothing transformation, that's like the identity. So if you're thinking about matrices, for example, as a similar thing, if you multiply a matrix by the identity, you get the same matrix back. Similarly, if we do one of these transformations followed by the identity, or the identity first, this R0, we get the same transformation overall. So R0 is the special element which does nothing and is kind of like the identity. So R0 is like an identity, even though we haven't made precise what that concept is yet. Okay, what else can we see? Is it the case that the order of transformations doesn't matter or not? So if I take R90 times R180, I get R270. Okay, so that's and if I do R180 followed by R90, I also get R270. So it's definitely the case that for some operations, R180, R90 equals R90, R180. Does this hold everywhere? What if we go into, let's take H times R90 times R90. Well, that gives us H times R90 is D, but what is R90 times H? R90 times H is D prime. So that's not equal to R90 times H. Okay, so we say that operation is not commutative. Which is just a fancy way of saying the order is important. Okay, it is commutative for some particular choices, but it's not commutative throughout. Therefore, the operation itself is not commutative. Now, if this R0 is like a do-nothing operation, wonder if the notion of inverses from matrices also follows through here. So, if you think about matrices, if you multiply two matrices together and get the identity, we say that one is the inverse of the other. So does the same thing work here? If I take an element times another element and I get the identity, that means overall those two operations undo each other, and so one is the inverse of the other. And the way that we see this in our table is that we have R0 in each row and in each column. So for example, if I take R90 followed by R270, I get R0. And so R90 undoes R270. It's the inverse of it. Does every operation have an inverse? Well, let's say, what would the inverse of H be, for example? Well, H times H gives us R0. That's no surprise. If I take the paper, flip it over horizontally, and then do it again, I get back to where I started. So each of the reflections, these H, V, D, and D prime, they're all their own inverses, and we can see that by this diagonal of R0s here. And the rotations, well, the inverse of R0 is R0. The inverse of R90 is R270. Likewise, inverse of R270 is R90, and R180 is its own inverse. But every element has an inverse, and that is an interesting property. Each element has an inverse, which, as far as the table is concerned, it means there's an R0 in each row and in each column. Okay, now these notions of inverses and things and identities, we've not really well defined them. We've just sort of made some allusions to matrices. So in the next video, we'll actually define more carefully what a group is, what an inverse is, what an identity is, and we'll set up our 4 rules about what something needs to satisfy to be a group, so we can start talking about properties of them. Okay, so that's enough for now. That gives you a bit of a taste of a group that hopefully is a bit unlike things that you've played with before. There's a lot of interesting structure going on here. There's blocks of operations and all sorts of things that we'll delve into deeper as we go through the course. But for now, that counts as our intro, so we'll see you next time.